Hi everybody, today we're going to start chapter 8. It's a continuation of the study of alkenes, which are the double bonds, carbon-carbon double bonds, and we're really going to dive into the reactions in synthesis. And so it's important that you've mastered chapter 7, you've read the chapter, you've practiced the homework problems, because we went into a lot of detail about electrophilic addition, and so you're going to see the similar pattern mechanisms again and again in this particular chapter. So, like I said, mastering chapter 7 will help you greatly in chapter 8. It all ties in together. Another advice that I'd like to give you is that there's going to be a lot of reactions here. It's important you start practicing them now and not just memorize them, but understand how they work. And for the most part, I will show you mechanisms as much as I can. If the mechanisms are too complicated and are not going to help you at all, then I might show you tricks to remember it. And so you want to make sure you're just practicing these every day. And from here on out, even though I'll tell you, for example, a certain test covers, especially in 12B, a certain test covers, chapters 15, 16, and 17, for example. This material from chapters 7, 8, and 9, and so on and so forth will actually show up again and again on your future test. The reason why I say that is because you need to know these reactions in order to do multi-step synthesis, right? So you can't make a new molecule if you don't know how to use all these reactions that you're about to learn, okay? So it's something that you just don't learn for one test and then you forget it. You're going to be using it over and over and over for the remainder of 12A and throughout 12B, okay? So it's important you master it now. I think some students who struggled in 12B just didn't work as hard as they should have for 12A to really understand the material, and it just caught up with them. And so I want to make sure that I emphasize how important it is to stay on top of it, to ask me questions if, for example, something doesn't make sense, or, you want to, I can't remember this. Is there another trick you can teach me? Anything, I'm here to help you. So please ask those questions. But you have to put in the work and effort, reading the chapters, watching my lectures, obviously, and practicing homework problems, and coming to work sessions prepared and ready to go. Okay? So let's get started now. So the reason why this chapter is so critical, and you'll see it from here on out, is that there are diverse reactions of alkenes. You can start with an alkene and make any of these functional groups I'm showing you on this slide. We can make epoxides. We can make 1,2-dihalides, halohydrins, alcohols, carbonyls. It's just, there are so many reactions you can do. So it's really useful to have double bonds around. And so why are we learning this? Well, this is going to help us to start a systematic description of major functional groups. So as I teach you reactions, I'll say, okay, these particular reagents make a cyclopropane, that particular group, or these particular reaction makes a halohydrin, and then we'll talk about that functional group as well. So you'll get to have more practices with different functional groups. And now we're beginning to focus on general principles and patterns of reactivity that tie organic chemistry together. So remember, we're establishing structure, property, relationships, so you don't have to memorize everything, but you recognize the patterns to help you predict products. Okay. Now, before I start off with all the reactions, I wanted to show you how they prepare alkenes in the industry and in the laboratory. So this is kind of a preview of an elimination type reaction. We're actually going to study elimination reactions in detail with their mechanisms, everything in chapter 11. So at the end of 12A, we'll get to elimination reactions. But I wanted to show it to you now. So you are responsible for knowing how to make an alkene, but you don't need to know the mechanism yet. So alkenes are commonly made by elimination of, for example, a small molecule such as HCl or HBr from an alkyl halide. And this is called a dehydrohalogenation reaction. And to do a dehydrohalogenation reaction, you usually use heat and a strong base to do that. Or we can have a dehydration reaction where we eliminate water from an alcohol, and that requires a strong acid at warm temperatures. in order to do that. But remember that elimination reactions are just losing small molecules. So for example, here we lose HBr. And because we're working with potassium hydroxide, you get KBr and water in the end as a result. Ethanol here is just used as a solvent. And so we'll study both of them, acid catalyzed elimination and base elimination as well. So we'll get to that, but I just want you to know that that's the reaction we're using to make alkenes. But now I want to dive into the actual reactions. The first reaction I'm going to teach you is a halogenation reaction. I like to tell you the names. You can add them to your tables when you're organizing all your reactions. And like I said, start making your tables now. There's going to be a lot of reactions in this chapter. A halogenation reaction is just basically the addition of halogens, right? We can use bromine and chlorine to add to alkenes to give 1,2-dihalides, which is a very industrially important process. It's like a good precursor to other types of materials. And I just wanted to point out that you won't see fluorine or iodine. It's just fluorine's too reactive, iodine is too slow. And so we usually mainly use chlorine and bromine. Now, I'm going to go into the mechanism in a couple of slides, but I did want to show you first. Remember, in order to establish patterns, you have to know how to identify the nucleophile and electrophile, right? Because we're doing polar mechanisms in this chapter. I'm not really going into radicals yet with alkenes. That's more polymers and all that stuff later on. But anyways, when we do polar mechanisms, we always identify the nucleophile and electrophile. And right now, alkenes are always what? Good. They are always nucleophiles. And therefore, that makes chlorine what? It makes it an electrophile, which may seem a little weird, right? You may be thinking, well, chlorine's a nonpolar molecule, Dr. P. Like, how does that even work, right? Well, what happens, and you may remember from a while back, I taught you a word called polarizability. And chlorine and bromine are polarizable. What does that mean? Well, review over your notes from your former lectures, but polarizable means that we can kind of change the electronic structure based on nearby molecules. So for example, because ethylene's a nucleophile, as it gets closer to chlorine, the electrons on the chlorine closest to it kind of run away, right? They're like, repulsion. Right? They don't want to be anywhere near the double bond. So therefore, this chlorine technically becomes more partial positive, and the chlorine that's farther away from the double bond is partial negative. Okay? So those electrons, we're always in dynamic motion here, right? And so as something, for example, like a nucleophile comes close, that kind of pushes those electrons away due to repulsion. Okay? So we say that chlorine and bromine are polarizable, and we can see this effect here. Okay? Now, not only, I told you in the last lecture, when you're making your tables, not only are you looking at examples of reactants, reagents, products, that sort of thing, but you're looking for regiochemistry, which we're going to get more into again, and stereochemistry. Is the reaction stereospecific or not? And in this case, when we've done cyclopentene and reacted with bromine, we have found that the only product that's created is trans-1,2-dibromocyclopentane. So we exclusively get the trans product. So yes, halogenation is a stereospecific reaction. Okay? Only gives you trans, which is good. You only get one product out of it. But that doesn't really make a lot of sense. Or initially when they first found this, they were like, well, why does that happen? Because in their mind, what they thought was happening and what you may predict is you might have been thinking, well, there's a carbocation intermediate, Dr. P, just like we learned in the previous chapter with electrophilic addition of HBr or HCl. And so maybe you had something like this where there's a carbocation and you said, well, the bromine could come in from the top or from the bottom, so you would get a mixture of products, right? 50 trans and 50 cis. But that's not how it works out here, so the intermediate must not be a carbocation. Because carbocations, remember, sp2 hybridize and they're planar. So we would get a mixture of products in this case, but we don't. So, scientists back in the day did a lot of studies, and what they found happens is, and I'm talking mainly about bromine, but same thing with chlorine, they find that we get this cyclic intermediate called a bromonium ion, which is pretty neat. And that helps us to explain why we get only trans addition and that stereospecificity. Okay? So what happens is the double bond attacks the bromine and kicks off that bromide, but immediately these electrons come back down to form the cyclic bond here, called a bromonium ion. And so I want to go through that particular mechanism, and I'm going to use a different starting material than what's in your textbook, because I find that the textbook, the starting material they used was symmetrical, and if it's symmetrical, it makes your life easier. But I wanted to show you the mechanism if your alkene isn't symmetrical, right? A little bit more challenging, right? And now that you just finished stereochemistry and master that material, then I feel like you're up for this challenge. Okay, so I'm going to give you kind of a little bit more challenging example. So remember, I'm going to draw my nucleophile or starting nucleophile in red. I am going to do methyl cyclohexene. And I'm going to use bromine, but remember you can do the same exact mechanism with chlorine, and I challenge you to do that. It would be good practice to do on your own. And so remember, the first step of the mechanism is that the nucleophile always attacks the electrophile. I'm going to use my green arrows for that. So nucleophile attacks the electrophile, kicks off the bromide, but immediately these lone pairs come back in to make a cyclic intermediate. Now, when we make a cyclic intermediate, those particular bonds here, it's going to be sp3 hybridized, right? So I need to have two in the plane of the paper, one bold and one dashed, right? So if it's cyclic, that means the bonds have to be on the same face of the ring, right? So I normally put my cyclic intermediates on the top face, so bold, but it doesn't matter which way you decide to put them. But they need to be on the same face because it needs to be a little cyclic structure. You can't have one pointing up, top face and one bottom face. You can't close the ring that way, right? So I'm going to get my green here. And this is that new bond that was formed here. And I'm making my cyclic intermediate on the top face. With the bromine here, that bromine still has two lone pairs. It has a +1 formal charge. What does that tell you about the methyl group? Is it on the top face or on the bottom face? It has to be on the bottom face now. So I'm going to draw the methyl group on the bottom face, and this is where you have to really keep track of your stereochemistry. So if you struggled with stereochemistry on the previous exam, make sure you come and see me or practice. I'm going to give you lots of different examples. The hydrogen also must be pointing down, right? Because these are sp3, two in the plane, one bold, one dashed, right? So this is called the bromonium ion intermediate. And we can put brackets around it. We also created a bromine ion that I will also draw here. It's going to come back into play. Okay, so this is the reason why I wanted to show you an asymmetrical intermediate. Now, the bromide is going to want to come and attack. The bromide, is it your nucleophile or your electrophile? It's definitely your nucleophile, right? The bromide is your nucleophile. Now, the bromonium ion is your new electrophile. Remember, this was nucleophile. This was electrophile. Make sure you can identify them. This is your electrophile because overall it's kind of like a positively charged electron-poor species. And if you were the bromide anion, where would you want to attack? Now, many of you may have said you wanted to attack from this side, right? You're probably thinking sterics, right? And that's a good way to think, but that's not how this mechanism operates. The bromide does want to attack from the opposite side of the cyclic bromonium ion. It doesn't want to go anywhere near the cyclic bromonium ion. It wants to attack actually from the bottom. So it's going to attack here on the bottom face, even where that methyl group is located. And then these two electrons go onto that bromine. Okay? So the bromide attacks the more substituted side. And don't worry, I'm going to write that down so you can have those notes with you. The bromide attacks on the more substituted side opposite from the cyclic intermediate, opposite face. Okay? So let's go ahead and draw the structure that we get. When bromide attacks there, it's attacking on the bottom face, so what happens to the methyl group? It gets pushed up to the what? To the top face. So the methyl group gets pushed up to the top face. And the hydrogen's still on the bottom face. But the bromine is popped open here, and how many lone pairs does it have? It has 3 lone pairs now, and therefore a neutral formal charge. And there's a bromide on the bottom here. And it also has how many lone pairs? 3 lone pairs. Excellent. Okay? So let's talk a little bit about the nuances of this mechanism so that, if I gave you a different starting material, you understand how to approach the mechanism and not just try to memorize, do I get trans or, does it go on the more substitute side? Like, how does this work, So first thing first, back over here, some things that I wanted to point out is that the incoming bromide nucleophile attacks the more substituted carbon on the opposite face of the bromonium ion. The reason why it does that is because the bromonium ion in solution almost behaves like a carbocation in a sense. Okay, so the bromonium ion like a carbocation. What you can imagine what's happening here is as the bromide comes to attack, the bromonium ion starts to open up already and leaving kind of like a carbocation, somewhere here. It could break open here or here, but it prefers to break open so that the carbocation would end up on the more substituted side. So I always tell my students, in order to remember the regiochemistry here, that bromonium and chloronium ions almost behave like carbocations, where in the second step, the incoming nucleophile will attack the more substituted side. Okay, and that's something for you to remember because I know that's a little tricky. In addition, we have over here, we always have trans. We make a trans 1,2-dihalide. So this reaction not only is regiospecific, it is a stereospecific reaction. Okay, and you want to make sure that your bond angles are good and that you have, nice bold and dashed lines. Okay? Now, sometimes students are like, well, how did they know that there's actually a bromonium ion? It doesn't seem like something would be very long-lived. But basically, what they did was a scientist named Ola showed that the bromonium ion is stable in liquid sulfur dioxide and antimony pentafluoride and was very stable in that solution. I imagine what they did was NMR spectroscopy, although I'm not 100% sure. I've worked with antimony pentafluoride and sulfur dioxide at really cold temperatures in the NMR, and that stuff is really scary. Antimony pentafluoride is a superacid, so you need to work in a vacuum hood. Once it's in the presence of oxygen, all things are crazy, or moisture in the air, it's just not good. But it is able to stabilize the bromonium ion for them to study it. So, and like I said, I imagine through NMR spectroscopy, which we'll get to in the near future. Okay. So not only can we make 1,2-dihalides or trans 1,2-dihalides, we can make something called a halohedron, and that means that the double bond we add not only a halogen but also an alcohol group. So you can see that these particular halohedrons are going to be really important. They're actually good precursors to future reactions that we will be doing, okay, or like to other functional groups we will need. So this is going to be a really good reaction for you. Basically, you react your double bond with bromine or chlorine and using water as a solvent, so lots of water. And water is actually going to come in as a competing nucleophile. So on the next slide, when we get to that step and you're like, but we have a bromide and we have water, which one's actually going to react? Well, water's a better nucleophile than bromide, but there's always a chance of mixed products, right? We might get a little bit of the bromide to attack to give the trans 1,2-dihalide, just like in reality, right? But I'm showing you the major organic product from these reactions, okay? So water actually is a better nucleophile than bromide. Reason being is that bromide has an octet, and these halides are very stable and happy on their own with that octet. So they make what we call good leaving groups, like they get out of the way, but not as good nucleophiles. Okay. So I wanted to show you the same reaction, or like this reaction using the same starting material so you can compare and contrast. So starting off with methyl cyclohexene. The first step of this mechanism is the same as the one that you saw before, where the bromine is attacked by the double bond. So the double bond and goes like this, kicks off the bromide, and then comes back here. So you need that third arrow so you can illustrate to your audience that you made a cyclic intermediate. So we get the same intermediate we've done before. Probably can beat me to it. So therefore, I'm going to have the methyl group on the bottom and the cyclic intermediate on top, just to be consistent. Remember those two lone pairs and that +1 formal charge. And we have the bromide that we also made, so I'll draw that there. But in addition, we are running this reaction in water. So I will draw water like so. Okay? Even though water is a nucleophile, because I just want to be consistent with the colors here, keeping it red, I'll just draw water in blue then. So just to remind you, this is now your new electrophile, and this is your new nucleophile. It's a better nucleophile than bromide, so that's the one I'm going to use to react. And just like you saw before, where do you think the water is going to want to react? On the more substituted side or the least substituted side? On the more substituted side. Good. So this water is actually going to attack from the bottom face and pop open. Those 2 electrons go on to the bromine. Let's go ahead and draw that intermediate. First, I should put my brackets. And then I will go ahead and draw that intermediate. Maybe you can beat me to it. And because the bromine, the water is coming in from the bottom side, that means the methyl group is on top. Got pushed to the top. The hydrogen's still on the bottom. The bromide popped open, that bromine now is on top, and the water we're going to find is on the bottom. So bromide or bromine has now how many lone pairs? 3, it's neutral. And water has how many hydrogens? 2, and 1 lone pair. What's that formal charge on that oxygen? It's a +1. Okay? So don't miss this step. This is what happens here. This is not the final product. We know the final product has an alcohol, not a water hanging off of it, right? So something has to come off and pull out that proton. And this is a common theme that you're going to see in lots of mechanisms, especially when water comes and attacks, and then a base has to come in and deprotonate it to make it into its neutral alcohol. Okay? So some sort of base is going to come in. Now let's think about our solution. What do we have in there? We have bromide. Is bromide a good base? No, it comes from a really, really strong acid, HBr. So its conjugate base is relatively weak. But what else do we have in solution that could act as a base? Hopefully you said water. Water can act as a base, and it's going to be very common we see it act as a base. So I'm going to bring in another water molecule to act as a base to pull off a proton. So water is going to come in and pull off one of these hydrogens and put those 2 electrons onto that oxygen there. And so now let's draw our products. Kind of redrawing everything. It really hasn't changed. And now we have how many lone pairs on oxygen? We have 2. We have an alcohol. And we've created what else in solution? We've created H3O, right? H3O, and what's that formal charge? Plus. We've created the hydronium ion, right? And the hydronium ion is just essentially a proton, right, or protonated water. And so if we have the hydronium ion solution and we have the bromide in solution, essentially these could combine to make HBr, right? So HBr in solution dissociates into the hydronium ion and bromide, right, into protons and bromide ions. So that's the product. We end up making the byproduct of this reaction is an acidic solution. And you may be like, well, I don't really care about that. I care more about the organic product, the final product here. Although that's really important, it's also important to know what's the pH of your overall solution. Is there something you can do to neutralize it? For your safety, maybe, for example, you don't want any of that residual acid to carry over to the next step in your multi-step synthesis. So it's important you know your byproducts. So when I ask you to predict products of the reaction, I'm expecting everything that I'm showing you here, okay, including the little guys, okay? Your textbook just writes HBr. If I show you the mechanism, then or if I ask you to show me the mechanism, I expect you to show me the hydronium ion, the bromide ion, just kind of the formation, just like I'm showing you here. And I do prefer that you use colored pens. It'll make your life so much easier to visualize. Sometimes students, if they don't use colored pens, they try to predict products or design their own multi-step synthesis, and then they end up not like getting too many bonds in their products or not enough, and it's just like if you use colored pens and if you number, and you won't lose anything, right? It'll make sense. So just keep track of it. Hopefully that's as visually appealing. Notice that the water attacked the more substituted side, like we saw in the previous mechanism, and that the alcohol and the halogen are trans with respect to each other. Remember, this is a stereospecific mechanism or type of reaction. Okay. Now, bromine is kind of dangerous. I've worked with bromine before. It's really bad for the respiratory system. You have to be really safe with it. So in the laboratory, a lot of people use NBS instead, which stands for N-bromosuccinimide. And that helps us to produce bromine in small quantities in solution. It's a much safer source. And usually we have to do, once again, bromine or NBS, water, and the solvent they use is dimethyl sulfoxide. So the structure of that solvent looks like this. This is a really good solvent for you to put in your list of solvents. It's what we call a polar aprotic solvent, and I'll teach you all about that later on. But once again, like I said, just getting familiar with the acronyms, the names, the structures of solvents is going to be helpful. But anyways, so I won't go through the mechanism of this. It does kind of involve radicals and stuff. I actually do go through NBS mechanism. I believe it's like in chapter 10. So it's coming up soon. I want to save that for now, but you do need to know the structure of NBS and then how it's used for. Okay, it's just another source of bromine. And if for example, I have a question on the test where I ask you to predict the products, you need to know what this does, right? Mm-hmm. Now, a really important thing to be able to make from alkenes is alcohols, right? Alcohol is going to be a very important functional group. And this is called a hydration reaction, right? Hydration. Hydration of an alkene is the addition of water to give an alcohol. In the industry, acid catalysts are used at high temperatures to make, for example, ethylene to ethanol. Like I said, at very high temperatures. And so I wanted to go through that mechanism with you. Now, it's an acid-catalyzed reaction, and anytime you hear acid-catalyzed reaction, I want you to immediately write down the hydronium ion. Because acid-catalyzed means a strong acid, and strong acids dissociate into that hydronium ion solution or protons in solution. Okay? This is definitely the nucleophile. This is definitely the electrophile once you have that. So as you can imagine, the double bond is going to pull off the proton. Notice how it doesn't attack the oxygen. Sometimes I get students make that mistake, and they're like, oh, but oxygen has a +1 formal charge. Well, which atom is more electronegative, oxygen or hydrogen? Definitely oxygen. So the double bond prefers a hydrogen, not the oxygen, even though the oxygen in itself is electron poor. Okay? So this pulls off the proton. These electrons go onto the oxygen here to make what? To make water. Right? So, and what kind of intermediate do we get? A carbocation. And where does the carbocation want to go? It wants to go on the more substituted side. Good. So before we already had a hydrogen here, a hydrogen here. Now we have a hydrogen going on the less substituted side. Right? And we created water in solution. And that's what we have to work with here. Which one is definitely your electrophile? Your electrophile is the carbocation, good. And which one is your nucleophile? The water. The water is going to act as a nucleophile here. Okay? So water is going to come in and attack that carbocation. Notice how I'm not really showing stereochemistry here. We don't really have to worry about stereochemistry here because in the end, for example, the product that we're making here is not chiral. So I don't have to worry about it. But do remember that because it is a carbocation, water could attack from the top and the bottom. So if you end up making a chiral center, then you need to show both products. Okay? Okay, so let's show that intermediate that we've created. And that oxygen has one lone pair and a +1 formal charge. You've seen this before, this pattern. What do you think is going to happen next? Water is going to come in and act as a what? As a base. Good. So let's draw our water molecule in. Our water molecule is going to come in and act as a base to pull off the proton and push those electrons onto the oxygen. And now let's draw the products. We have an OH. And what else do we make? The hydronium ion. And that's important, especially when you're showing mechanisms, because I told you this mechanism is an acid catalyzed mechanism. When I say catalyzed, what comes to your mind? Catalyzed meaning the reaction is faster, and catalyzed meaning we can regenerate the catalyst. That's the idea. You only need small amounts. We notice we start it with the hydronium ion, we end it with the hydronium ion. So it's a catalyzed reaction because we regenerated our acid catalyst. Okay, that's important. You regenerated your acid catalyst. Now, like I said, this is more industry, and it's at really high temperatures. It's just not really fun to work with. So we have an alternative for like smaller scale in the laboratory, and that's called oxymercuration. It's the laboratory scale hydration of an alkene. We use mercury acetate and THF followed by sodium borohydride as our reagents, and it does give us Markovnikov orientation regiochemistry, and it goes through something called the mercurinium ion. Very similar to the bromonium ion. Okay, so I'm going to go ahead and do the mechanism and have you help me derive it. Try to predict it before we finish it. So we have the double bond, and we also have something called mercury acetate. It looks something like this. We're going to abbreviate it like that. You can say AgOAC2. Okay? AC meaning acetate. So it looks like Ag, like this. So I'm not drawing the full structure in the mechanism because it could get a little bit crowded. But that's what the reagent looks like. So it has the conjugate base of acetic acid kind of connected to it, the acetate. And transition metals are good Lewis acids or electrophiles. So they have those empty d orbitals that can accept more electrons. And so the double bond is going to attack the mercury. And when it does that, it kicks off one of the acetates, but then, kind of like the bromonium ion, it comes back and attaches itself to make a cyclic intermediate. So I'm going to make my cyclic intermediate on the top face, so that methyl group is on the bottom. The hydrogen that's already there is on the bottom. So we'll make the mercury on the top face here. Okay, it's like a +1 formal charge. We are adding water in the process. So water's going to come in and act as a nucleophile, kind of like what we've seen before. And where do you think the water's going to attack? On the more substituted side. Good. Like I said, it follows the Markovnikov regiochemistry. It's going to attack the more substituted side, pop open that mercurinium ion. That was the intermediate we had. That pushes the methyl group to the top. Okay. We have the water on the bottom face of the ring. I'm supposed to write that in blue. And then the water in blue. Okay? I know many of you are probably thinking, water's going to come in and act as a base and pull off that proton. Well, we have another base in solution that we kicked off. We have the acetate. And the acetate's actually a pretty decent base in a sense that acetic acid's a weaker acid. So water or acetate come in. I usually tell students acetate comes in and pulls off the proton. But if you use water, that's also okay because this is all dynamic, right? So much is happening all at once. So I will draw, one second. So I will draw, first I'll write the brackets. And water will, or acetate will come in and make acetic acid. So this is a conjugate base. And it will come in and pull off a proton to make acetic acid. Like I said, water is probably doing the same thing as well. Pull off that proton, those electrons go there. Kind of draw everything there that hasn't changed. And we have the blue. So now we have OH here. those 2 lone pairs. One of the byproducts we made, it's like acetic acid or an acidic solution, right? And we still have the mercury on there though. You're like, oh, we got to get rid of that, right? We're almost to the product where the alcohol's on the more substitute side, but we have to get rid of the mercury, and that's in the second step. So in the second step of this reaction, sodium borohydride is added. Now this is going to involve a radical type mechanism, and your textbook doesn't show it, and if you try to find it online, it's kind of intimidating. It's a little challenging, but I tell, go ahead and do it, check it out. But basically on this one, I kind of tell students, don't worry about the mechanism. Simply, sodium borohydride is a reducing agent. And we're going to talk a lot about reducing agents and oxidizing agents in terms of organic chemistry. I know you've done it already for general chem. But reducing agents tend to add a lot more hydrogen. So basically, it's going to come in and replace the mercury with a hydrogen. Okay? So the final product, which I'm going to show over here, looks like this. We have a hydrogen there. So if you get this alcohol, and it's on the more substituted side, so this is the hydrated product of it. And like I said, once again, this is a mechanism you don't have, you don't need to know, you're not required to know. It involves radicals, a little bit more complicated. But we know it reduces it, removes the mercury, and replaces it with hydrogen. Okay? Now, I've taught you a reaction where hydration goes on the more substituted side, but what happens if I wanted to go on the less substituted side? I want non-carbonyl addition. Well, we can do a reaction called hydroboration to do that for us, because it goes through a completely different type of mechanism. And borane, or BH3, is electron deficient. It's a Lewis acid. Remember, the Lewis dot structure for BH3 looks like this. Doesn't have an octet, so phenomenal Lewis acid or electrophile. Borane basically adds across the alkene to give an organoborane intermediate. And then we have an oxidation step here that converts the BH2 into an OH, okay, into an alcohol. So this is going to be more of an oxidizing agent. Hydrogen peroxide or any of those peroxides are good oxidizing agents. Okay. Now, I did want to show you that in reality, when we're studying this, if we have, usually we add a lot more alkenes than we do BH3. So this could therefore, if we have 3 equivalents, we could make a trialkyl borane intermediate. And so when I show you the transition state on the next slide, I'm only showing 1 addition. But this is what's happening in solution. In reality, it's like 3 additions at a time. But you're not responsible for drawing a crazy intermediate like that where all 3 alkenes attach to the borane and then you show the complex and all that stuff. Like, you don't have to worry about it. But I wanted to show you because it is in your textbook. And that we use the oxidation with the alkaline hydrogen peroxide and water to produce the alcohol derived from the alkene. Okay? Before I move on, I wanted to tell you real quickly about steps and things like that. So for example, in the first one, I said that you added mercury, acetate, water, and usually it's done in THF as a solvent. The second step you do in sodium borohydride. It is really important you know when a reaction needs to have multiple steps. I will not accept it if you leave out the numbers. And you may be like, well, that is so picky, Dr. P. Why would you do that? The reason why that is because if you throw the sodium borohydride in with the mercury, bad things will happen. Okay, so it's important that you know in the first step you only add these reagents and solvent, and you let it set, you let it react maybe overnight, and then you come in and do the stepwise, the second step, sodium borohydride. Okay? It's important that you know the numbers of your steps, and that's what's going to take the most practice. I think initially students struggle with the number of reagents to learn. I always found that recopying my notes and recopying the reactions and talking myself through it helped me out greatly, and I hope it does for you too. Okay? So for this one, the first step is BH3 in THF. The second step is hydrogen peroxide in water, and it's alkaline solution, so a little bit of base. Okay? Those are the reagents. Now, this hydroboration reaction is also another stereospecific reaction. The hydrogen and the OH will add with syn stereochemistry to the same face of the alkene. It's opposite of anti-addition. And the regiochemistry is non-Markovnikov. Okay? So what happens is that the BH3 adds to the same side. So this is what they're talking about when they say syn stereochemistry, same side, syn. And then when the hydrogen peroxide and alkaline solution comes in, it replaces the BH2 with the OH. Okay? So this is definitely a stereospecific reaction. I think this one's a little bit more challenging than the previous one, but I'm going to show you the transition states to hopefully help you remember it. Okay. So basically, start with my red. And we have BH3. And I'm going to show you the transition state that's proposed, not necessarily the intermediate that I just showed you on the previous slide. You did see it on the previous slide, but basically the double bond attacks nucleophile to electrophile. And I'm going to have the cyclic alkane on the bottom. So I have that. And I have to make the bonds a little bit longer so you can see it. The BH2, remember there was a BH2 on one side, right? It's pretty big, right? So where do you think it wants to add? To the more substituted side or the less substituted side? It wants to be on the more substituted side. Oopsie, I was supposed to draw that in blue. And then the hydrogen over here from that BH3 is still kind of attracted to it. So this is the proposed transition state. Remember, we cannot isolate transition states. We can only use a lot of experimental evidence and theory to help support it. But basically what we're saying is that there's a cyclic intermediate or organoborane intermediate kind of forming here, and that the BH2 is forced to go on the less sterically hindered side. There's no carbocations here. We don't have to worry about that. So sterics plays a role. So it has a lot to do with sterics for why that BH2 wants to be on the less substituted side. And it's syn addition, that whole complex adds to the same face. And then in the second step, when we add our alkaline hydrogen peroxide and base, right, we just simply convert this into an alcohol group. It oxidizes it. bonds. Green pen. This is a hydrogen, and this is our OH. Okay, and we get syn addition with the hydrogen and the OH, right, to add it to the double bond. So a stereospecific reaction. All right. So that gives us non-Markov regiochemistry. So the OH goes on the less substituted side, and syn addition. The last reaction I want to talk about for this lecture, and then the second part, or the second lecture, I'll kind of keep going through all these reactions. But I want to talk about the addition of carbenes to an alkene. Now, what exactly is a carbene? Kind of a fun name there. It's referred to as half an alkene. Carbenes are electrically neutral, so no formal charges, with 6 electrons in their outer shell. So they are desperate to react, and they don't have an octet. And so we have to create these particular species in situ. We have to make them in solution while we're reacting. They're not very long-lived. You're not going to buy a bottle of carbenes from Sigma Aldrich, right? And the addition happens across double bonds symmetrically. So this is also another stereospecific reaction. Okay. It makes cyclopropanes. Now, how do we make a dichlorocarbene in solution? We start with chloroform and a strong base. So chloroform is CHCl3. And we have a strong base coming in. And it's going to pull off the proton. It's going to pull off this proton here, and therefore those lone pairs go onto the carbon. So let's go ahead and draw the intermediate that's formed. We have a lone, we have a lone pair there. Lone pair on that carbon, and then the 3 chlorines. And that carbon has a what kind of formal charge? A -1. Now the next step is a spontaneous loss of a chloride. Because remember I said halogens, when they go into their halide form to chloride or bromide, they're happy, they're great leaving groups, because then they have an octet and they'd rather be on their own. So what ends up happening is that we get spontaneous loss of a chlorine. Those 2 electrons go on to the chlorine, and we get a chloride off that now has that -1 formal charge, and we are left with carbon with 2 chlorines and a lone pair. Okay? That's how you would make it in situ. You need chloroform and KOH. Those are the reagents that you would see to make a carbene. And a dichlorocarbene more specifically. Okay? It's a stereospecific reaction. So for example, you see these reagents here, and you can see that we have the dichlorocarbene there. It started off as cis. So normally what I tell students is usually what it will look like here is they'll have something. Usually we make alkenes flat, right? We're like, oh yeah, it's flat because it's trigonoplanar, that makes it easy, but we want to make sure we maintain that specificity or that stereospecificity. So what I tell them is just to make the ones that are going down, you're going to rotate it kind of 90 degrees towards the back. So make these going down coming at us as we rotate these to the back. So that when you plot this on here, when you predict the product, that reaction, you maintain that stereochemistry for that cyclopropane. Okay? It's a stereospecific reaction. Maintain that stereochemistry. And maybe you don't want those halogens on there, so an alternative to chloroform and potassium hydroxide is called the Simmons-Smith reaction, which gives you an equivalent addition of CH2 with that lone pair. The way we do that is the reaction of diiodomethane with zinc copper alloy produces a carbanoid species, which then reacts to make cyclopropane. Not going through the mechanism of this, but you do need to know these reagents. Ether is just a solvent, diethyl ether. And it's going to make a cyclic intermediate. It's still a stereospecific reaction because of that. And then the byproduct is just a salt, zinc to iodine. And yeah, so this reaction is pretty popular because in that way we don't have the chlorines hanging off of the cyclopropane. Okay? So go ahead and make sure that you're practicing your problems up until this point and reading the textbook. And I will finish up the lecture and all those reactions the next time around. And keep up the hard work, and I'll see you soon.